Hi guys, my name is Hari and this is Project Directory, where we'll be focusing on technical videos related to projects that I and the OSS community have built. I'm back with a bit of a technical video today, and we're going to be learning how to build our own text editor from scratch. Obviously, if you have watched my previous videos, you know by now how much I value a good text editor. So here's a simple video on how the process of building a text editor goes through its stages. This is going to be a multi-part series, and part 1 of this series, which you're watching right now, revolves around project setup, data modeling, and a cool design pattern of Rust that I found, and how I repurposed it for a specific feature of the text editor, which is Modality. You should know that we are going to learn to do this together, because I'm just starting out as well with the project. And you will get to see how I take a project myself through its phases, and you'll see me struggle a bit too, but hopefully it teaches you how to create anything by just having fun and being curious while doing it. So let's begin. Well, let's start with clearly defining what we're building, which is a text editor. Not a code editor though. That comes with its own set of complexities and unnecessary features that might take its own video. It's always good to narrow down the basics of what your software must do. In our case, it just has to behave like a Notepad clone on the terminal. Maybe I'll give it different modes like Vim and Helix, cause I seem to like those. Real quick, for those who don't know what a Modal text editor is, we have different modes to do different things like navigation, editing, and selection. And most of the common Modal editors are centered around using your keyboard more. Vim, for example, just completely doesn't support the mouse at all, because all the actions have a respective keybind on the keyboard to do the same. It might seem less intuitive at first, but eventually, a person who knows most if not all of the different keybinds works faster than the average person who uses both a mouse and a keyboard to maximize productivity. But for now, we'll focus on 3 things: creating and opening a document, writing and deleting characters, and saving the document. Later, we'll model our data better to do more, but let's just start with this much. Also, I'm assuming at least a basic level of understanding on the working of the Rust language, because I'm not going to go over the language and its syntax, but I'll try to explain what exactly that part of the program is supposed to do. I saw this project on GitHub about a text editor built in Rust called Hecto, where this person built a whole Vim-like text editor from scratch using Rust. It's not Helix with a whole suite of IDE tools, but it is something comparable to what I want to build on my own. Turns out they had a whole guide written on how to do exactly the same, so I think we'll follow the same for a while until we see something that I don't understand and then go raw from there. Starting with the setup, we can skip all that. I have a Rust project already set up. Entering raw mode. Yes, so now I've put my terminal in raw mode before in my project that eventually became the name of the channel, Project Directory. That project was about creating my own PowerShell-like terminal. How it works is that your terminal emulator by default handles many keybinds and mouse inputs of your input devices, and leaves very few inputs from the user to apply to terminal-based apps. Raw mode puts all the control of your terminal to the program that you are running. We'll use crossterm for this. It's just a low-level implementation to remove control from the terminal emulator and place it into your program. In Golang, you would use something like the GoKilo library. Right, so now that we have all that set up, the main reason we needed raw mode was to read a key event or a key input. In our case, the Q key, so that should, when pressed, quit the program. Obviously, Ctrl plus C wouldn't work in raw mode, so let's write the code for it ourselves. The next chapter again goes in detail about language specific implementations. We're not going to go into all that right now, maybe later. Now let's get into the interesting part, modeling our business logic. To explore what business logic means in our case, we need to look at how real-life data is modeled in any program. Now the easiest case of this is to show a real-life object and model it using any object-oriented program. So here's a Java file and I'm going to create a simple class to represent a fruit. Obviously this is one of the examples that school or college teaches you. They ask us to use any real-world object but always give irrelevant or mundane examples like a dog, fruit, animal, etc. Let's take a more fun and nuanced example. Imagine we're representing a Pokemon. Weird example, I know, but bear with me here. This is how a simple class for a Pokemon would look like. And this is how Pokemon are represented in Pokemon Essentials, an open source project which is written in JavaScript. This is great, pretty detailed, but almost the same. This is how objects in real life are represented within a program, and we are going to do that for ours as well. Now, since Rust isn't an object-oriented language, we represent data using its type system just like any other functional programming language using structs and enums. Using these, let me start with defining the most basic struct in our project, the line struct. Now, why did I make a separate struct to store just a line? We know that in object-oriented programming languages, data and their methods can be stored in one container called their class. Rust doesn't have classes, but it does have something similar to let us implement methods on its types. These are called implementations. In many languages, this is called an abstract class or an interface, but what it essentially allows us to do is to define functions that work on the variables defined in its particular type. This will be very useful later when we implement more functionality to our line struct. For now though, let me just include a new method. I can create an implementation using the impl keyword. Next, let's begin to model an open document. This essentially should store a list or an array of lines and store metadata about the open document. Let's just name the struct as document. Yes, so a simple document that stores all the lines in a vector and a simple file format metadata about the open document. Now here's where it gets a bit interesting. I want to implement more methods on this struct to get specific data out of it. So let's do that. I'm thinking I need methods to get the line length of a specific line, the line count, the character count. Let me create an impl block and write those function signatures. It's a good idea to reason yourself about what each function should do and how it is achieved using your programming language. So I'll leave that to you guys to figure out. Let's not discuss about the syntax more, I'll just add the implementations. Let's move on. In any modern text editor, there is this concept of tabs or multiple open documents at the same time. In terminal text editors like NeoVim and Helix, they are called buffers. And we can have multiple buffers open at the same time. We also have an initial empty buffer to directly type into. I want to include this as well into our app. And that leads us into the Editor Struct. The Editor Struct represents a running instance of our app which manages the multiple running buffers, or in our case, variables of the document struct. So let's build that. We'll also implement a few methods to work with the Editor Struct, starting with new. This is as simple as adding two functions to switch buffers forward and backward by increasing and decreasing the current focused index value respectively. What essentially this code does is that it checks first if multiple buffers exist to switch between. If yes, then it checks if the user is already in the last open buffer, and if that's the case, it goes to the first buffer, and if not, it just moves to the next buffer index. The switch backward function does the opposite. Notice that the new functions take a mutable reference to the variable that we are calling from. This is because we are modifying the variable itself. We require a mutable reference here. Now comes the concept of modality. In my previous video about Vim, I explained that Vim is a modal text editor. That means it has different modes depending on what exact action we want to perform. Normal mode for moving around the document and performing quick actions like cut, copy, paste. Insert mode for inserting text into the document. Visual mode for performing actions on selections. And command mode for executing editor commands. So I also want the editor struct to store the state of the editor, which can be 1 and 4, navigate mode, edit mode, select mode, and command mode. Let's add that in the form of an enum so that we can make invalid states unrepresentable. Our new editor struct looks like this, with a state variable to track its current state. Great, so now we can just include methods to switch between them, like so. Our current implementation for modality is good, but now we run into a new problem. There are still absolutely invalid states that can be represented using our current implementation. The methods to switch between each mode is accessible from any mode. But for someone who in the future might make modifications to this API, I want to enforce that some modes cannot be accessed when I'm in a specific mode. So how do I make it so that few methods are not available to use when the editor is in a specific state? One possible solution is to create separate structs for each state and implement different traits for all of them. And write their implementation like this. We can then do this to use them together like this. Now you can already see that we've solved one solution just to introduce another problem. The problem with this approach is that the reassignment leads to unnecessary cloning of the data and a lot of duplication of code. Fortunately for us both, there is a better way to do this in Rust. There is a brilliant video by Let's Get Rusty where he builds a simple password manager. He takes us through the stages of representing this exact state problem. This is one of the times where Rust's rich type system comes to our rescue. First, instead of spending memory to represent states in the struct or creating multiple structs to represent valid states, we'll go back to our enum example, and this time instead of using an enum, we'll be using a zero cost type. We start by first representing each of our editor states as their own empty structs called unit-like structs. The Rust standard library includes a provision for us to create and use zero cost types, which are types that are subtracted away during compilation, so they don't take up any real memory space unlike an enum to represent. We use the phantom data type from the standard marker module. This allows us to tell the compiler that our editor struct possesses a certain type state, even though we don't actually store a value of that type in memory. It's strictly a compile time marker. So we modify our editor struct to be a generic over a type state. When we create the editor, we initialize it in navigate mode like this. The phantom data consumes no space, but it allows us to define implementations specific to editor in navigation mode, editor in edit mode, and so on. Now, how do we switch modes? Okay, here's where the code gets a little bit interesting. Rust's ownership system is so neatly designed that it makes our problem solvable so much more efficiently. In the previous bad example, we might have had to either clone data or restructure it. Here, we can define a transition function that consumes the current editor, which means it takes ownership of the current editor, and returns a new editor with the new state, moving all the heavy data like buffers, vectors, without cloning it. This is incredibly efficient. It compiles down to a no-op essentially, just reinterpreting the type. Now we can implement logic that is only valid for specific modes. For example, navigate mode should handle movement keys and mode switching, but shouldn't be able to insert text. And edit mode gets the ability to insert and delete characters. This way, editor.insertChar is a compile time error if editor is in navigate mode. We have successfully made invalid states unrepresentable. Finally, to communicate with the outer loop, which is the main function or the UI layer, about what needs to happen, like quitting, saving, or just redrawing, we can return an editor action enum from our input handlers. This gives us a clean API for the frontend. The frontend just calls editor.handleInput and gets back an action telling it what to do next or if the state has changed. And that's it for the core logic setup. We've gone from a basic struct to a robust type-safe state machine using Rust's type state pattern. In the next part, we'll actually hook this up to the terminal, handle real keyboard input, and start rendering our text buffers to the screen. I think. I don't even know yet. If you are interested in how you can build your own text editor, check out the top link in the description, which leads to the Hecto project by Philip Flenker that we've been following so far. If you are more interested in the Rust programming language and its paradigms, learn Rust using the free Rust book website. Link is again in the description. Thank you for watching and stay curious.